Now, this may be it's a little of a strange topic to cover here. And I mentioned for chapter 15 that I'm not going to cover all of the material in there. Most of it I am actually, but there's an aspect of waves on a string that I'm not talking a lot about, and I'm not going to talk much about. And in fact, the only reason I normally talk about this stuff is because when we are in the classroom and we have actual labs, there is a lab that involves tension on a string and standing waves. So I talk a bit about this now in anticipation for that. However, I am still going to talk about it, even though we're not covering that stuff in the lab. I mean, there may be something in the lab. Actually, I don't know. I haven't made the lab yet for this Friday. I could do that. So I'm not going to go through the derivation of this equation here, but your textbook actually does an excellent, really simple derivation of, and the idea is this: if you take a string, a rope of some kind, for example, and you snap it, right? What happens is when you snap it, you're imparting a vertical force well, let me put it this way. You're holding the rope. Say you're pulling back a little bit, so there's a little bit of tension in the rope. The idea is that there's some tension in the rope.
Are you screen sharing?
No, I'm not. All right. Jeez.
Yeah, sorry about that.
No. I'm sorry. I just I do that like every time.
It's fine. It was showing at first. It just dropped.
Earlier today, for my other class, I remembered. I said I'm gonna make sure I screen share, but then I didn't. I forgot to record. So whatever. That's not as bad of it. This is not as bad of it. Okay. Anyway, so yeah. So this equation here, the idea is that, imagine you have a rope that's tied to something, maybe, right? And the idea is that you snap the rope, and when you do that, you impart a force, and there's like a vertical force that gets applied, right? So what happens is it causes the wave to kick up, and it produces a pulse as the wave goes through. And what this equation tells you is the velocity, the transverse velocity of that wave, which is a function of the tension that's in the string and the mass per unit length of the string. This is mu down here, which we have. Mu is used for like a million things in physics. And we don't try not to repeat symbols and stuff, but we usually do repeat symbols when the concept here is far removed from the other concepts. So this is not related to coefficients of friction, and it's not related to magnetic dipoles, and it's not related to I don't know, the prefix symbol. What else we got mu for? Mu's used for something else. Well, there's some atomic physics that uses mu. But anyway, so so the F is the tension of the string, and usually we use T for tension. The problem is that T shows up a lot in these wave equations, and it means period, which already we changed that T from a P because the P showed up. So I mean, we got a very confused set of symbols here. But anyway, so the book has a nice derivation on this, but I'm not going to go into the details because again, the focus isn't really on material waves too much. I don't want to focus too much. All right, so based on that equation that you saw there, I have a question for you. Go ahead and throw into the chat here a letter. 4 strings of a musical instrument all made from the same material. They're under the same tension, but they have different thicknesses. All right, let's B. Because the idea behind this is that the thinnest string, all right, has the smallest value of mu, mass per unit length. And so the wave travels the fastest there. Fantastic. All right, so let's do some examples right off the bat. These examples are going to incorporate that wave speed And we're going to also revisit a lot of those equations we had from the last lecture so we can get a little more practice with that. All right, so here's our problem. A very long string, that's not that important, with a mass per unit length of 2 grams per meter. You're going to eventually have to put that mass per unit length in SI units because your tension's going to be in newtons. So you got to make sure things are in kilograms. Stretched along the x-axis with a tension of 5 newtons. It's not too bad. At x equals 0, it is tied to a 100 hertz simple harmonic oscillator that vibrates perpendicular to the string. So what does that mean? Vibrate perpendicular to the string means it produces transverse waves, which is all the stuff we've been talking about. A 100 hertz signal means the value for F is 100. Not the value for omega, it's the value for F. We got the amplitude. It's fantastic. The oscillator has its maximum positive displacement at x at t equals 0. That means we're using a cosine function for the wave function because that last sentence is an initial condition, and either you incorporate a phase shift or you use the cosine, because the cosine at x equals 0 and t equals 0 with no phase shift, hold on. Sorry. Everything's bugging me today. Oh my goodness, I gotta toughen up a little bit here. All right. So we're going to use our cosine function for that. We're going to write the displacement equation for the travel wave in the string. All right, so we have the amplitude. It's 2 millimeters. I'm going to leave it as a 2. What don't we have? We don't have K. But we could find that pretty easily. And we'd see. We need omega. Omega is easy to get. And that's it. So let's go figure out our wave speed, because we'll need our wave speed to figure out what the lambda is. So tension's 5. The value for mu is 0.002, and we end up with a speed of 50 meters per second when we put all the numbers in there. Now, the wave number k is going to be 2 pi over lambda. We're going to use our lambda times f, the frequency, equal to the wave speed to get that. So I substitute in for lambda V and F here. And so now the top portion here, 2 pi F, that's what omega is actually. So this is omega over V, which is another relation we actually had. We had, K equals omega over V was something we derived for. So let's put our numbers in here. F is 100, V is 50. We end up with a wave number of 4 pi. So we can start putting this together here. 2.0 times cosine times 4 pi x minus, and that's omega, but omega is 2 pi f, so that's 200 pi t, and that's it. That's our equation. That would explain what the value of the displacement of the wave is in any position in time. Great. Now, for part B, we're told to put the numbers in there. So at 5 milliseconds, what is the string's displacement at a point 2.7 meters from the oscillator? We just plug our numbers in. Just make sure that you got things in meters. Make sure that time is put into seconds. It's in milliseconds right now. And we put that through, and I got a value of 1.6 millimeters. That's what I got there. So the amplitude's 2, 1.6. So we don't really know what's going on with that. Either that could be going up or going down. The only way you know is to figure out, the derivative of this and see if the velocity is positive or negative. Other than that, so anyway, this was just another exercise in using those equations from last time, with the added information that we can throw in our wave speed by using that equation. All right, so I think I have another example right after that. All right, so this is a bit of an odd question here, but all right, so we have one end of a 2 kilogram rope is tied to a support at the top of a mine shaft that's 80 feet, 80 meters deep. What? All right, the rope is stretched taut by a 20 kilogram box of rocks attached to the bottom. Okay. Geologist at the bottom of the shaft signals to a colleague at the top by jerking the rope sideways. Great. What is the speed of transverse waves in the rope? All right, cool. Well, we got to figure out what the tension is in the rope. And we're going to make a simplification here because we're going to say that the tension is basically just due to the rocks. Now, I know that the rope has 10% the mass of the box. And so what I'll actually do is we can actually go back through this and try to determine how we would incorporate this if we wanted to include the mass of the rope. But it was so small that I initially did not do it. But it's nice to go back through the calculations and try to figure out how things might change. So that's good. All right, so based on just the mass of the box of rocks alone, we end up with a tension of 196 newtons. That's 20 times 9.8. All right, now, so we're going to have to work out what the speed of the wave is, so we have to get mu, right? Yeah. So that's the mass of the rope divided by its length, and so that's 0.025 kilograms per meter. We have all the information we need, so we're going to go ahead and put that in, and we get a speed of 88.5 meters per second, which is insanely fast. That's pretty nuts, actually. 88.5 meters per second is pretty darn fast. The amplitude of these waves must be pretty. It must be really hard to generate that speed, though. 2 hertz. Can you do that? 2 hertz. That's. Let me think here. That's back and forth in a half second. That's tough. That's tough. How much does this thing weigh here? 20 kilograms. I'm talking almost 50 pounds. You got to slug 50 pounds back and forth. We don't have the amplitude. It must be a very small amplitude. Anyway, I'm just thinking out loud here. All right. So that's the speed of the wave here. To get the wavelength, we'd have to divide that by the frequency at which you're oscillating this rope here, and that's just 2 hertz. So we end up with a wavelength that's pretty huge, 44.25 meters. And so that would be 1.8 wavelengths on the rope. Take the 80 and divide it by that. Now, here's the tricky thing about this. What will actually happen if you want to solve this, knowing that the rope has mass? It's a little bit more complicated because here's what happens: the tension in the rope wouldn't be constant. Right? At the bottom, the tension's 196, but at the top, it's going to be like 215 or 214 or something like that at the top. So if you put in, let's just put in the full mass, the 22 times 9.8 over the mass density is give you a speed of 93. So what that means is at the bottom, when the geologist is jerking the rope back and forth, that wave speed is 88.5, and as the wave travels up, it actually gets faster. Right? It gets faster. And so what happens is the wavelength's going to vary throughout the rope, but not by much, because look at this speed jump here. It was not very much. maybe 5% higher. That's about it. And so the wavelength, might be, because what, like, the speed's a little higher, that means the wavelength is a little lower. It would be like an average wavelength. So, yeah, it's hard to get a precise value on this if you include the mass of the rope. But you could see the range of values, right? That's the range of speeds, it'd be a range of wavelengths, and so on and so on. All right. Let's talk about the behavior of the wave here a bit. So again, we're still on material wave here. Imagine we have a string or a rope. And there's a couple situations that are going to happen when we talk about reflection of waves. This is going to come up in quantum. It's going to come up when we do interference, when we get back into optics, this idea of how waves change at boundaries. So in this example here, we snap our rope, the wave travels towards the wall. Now, the right side is fixed. It's a fixed end. And what's going to happen is when it hits that right wall, there's going to be a Newton's third law interaction that takes place. An equal and opposite force is going to be exerted by the wall on the string. And what that does is it inverts the pulse. And so that pulse gets inverted. The amplitude, which normally was above the string, is now going to be below it, and then it will continue to the left as it moves. So this is for fixed ends. What happens is, and this is what this is mathematically, this is a 180-degree phase shift is what's happening here. Now, the other scenario is when we have an end that's free, a free end. And for a free end, you don't have that Newton's third law interaction because the end can physically go up and down with the wave. And so what happens is if the end is free, the end can travel up, and then the wave simply is reflected back with no phase difference at all. It just goes back the same way. And so that will produce a wave that basically looks the same but traveling in the opposite direction. Now, if you imagine that you are oscillating the string, like it's set up to something that produces regular, oscillations. Then what happens is there's waves that are traveling to the right, and then regardless of whether you have a free end or not, the waves do reflect back. And so what happens is you have an interference that's going to take place. You're going to have a wave traveling to the right and a wave traveling to the left, and those two waves have to combine together to form some single wave, right? What ends up happening is when this occurs, you end up getting what's referred to as a standard wave pattern, where you actually have both destructive and constructive interference that's occurring on the rope, and at the same time. So let's go through the mathematics of it, and we'll talk about how things look. I'll talk about these nodes and antinodes in a moment here. All right, so this is taken from the OpenStax textbook. Your textbook has a slightly different derivation than what I'm going to do. I don't like the book's derivation myself. It's got, I don't know. I just don't. I don't. Not my favorite part of that book. Oh, okay. I guess I got that wrong. Okay, so the red wave is going to the left. Okay, so the blue wave's going to the right, and then the red wave's going to the left. So just imagine that you have, this is maybe some section, for example, of the standard wave pattern. Okay, and so you have waves going left and right. What happens here, and what you're looking at here are the waves at different points in time. So on top here, the waves happen to have the exact same phase, and so they produce complete constructive interference, right? And so the wave comes up like this. Now, we wait an eighth of a cycle later, And when we combine the waves there, we have a same wave. You notice the black, which is the combination here, is the same as the wave up here, but the amplitude's a little lower. After a quarter of a period goes by, the waves are undergoing a complete destructive interference. And so there's no black wave to see here. It's all completely eliminated. And then as we continue along, see how the pattern goes. Now look at how the black wave is going. The black wave looks like it's stationary in position, but it varies in time. So we could see the wave gets smaller in amplitude, it's gone, it gets greater in amplitude, gets complete constructive interference. When we get down, it starts to go back down. We have this cycle. So the result of these things is to produce what we call a stand-in wave. The wave looks stationary, it just is up and down. Okay. And if you haven't seen this phenomenon, I recommend just going on YouTube and type in stand-in wave and just watch demonstrations. I would show you that here, but I attempted to show a video to my 120 class, and it didn't go over too well. It just, when I have like my video editing software up and PowerPoint up and Zoom's up and Adobe's up and the computer is like on the brink of exploding. So anyway, but if you've not seen the stand-in wave behavior, definitely check that out. It's interesting. All right, so let's actually talk about the math behind this. I'm going to bring up a screen share, and I'm going to derive some stuff here. All right, so the idea is that we're going to have, oh, I want that to be a little bit thicker. Let's go with some thicker. How's that? That's a little much. I can live with that one. All right, so the idea here is we have our combination of waves here, right? We have, the wave that travels to the right is going to be some A sine. Did I go? Yeah, I do a sine. Kx minus omega t. And then you have another wave, so we'll call this 1 and call this 2. The other wave is identical with one little tiny difference, and the difference is that it travels. One second, I gotta get my thing here. This drawing tablet comes with a Michael Jackson glove for style, and because if your fingers touch the drawing pad too much, you get a lot of spurious signals, which we don't need. And this is going to be kx plus omega t. Remember, and that's what we do when we have a wave going in the other direction. If we want to combine these together, we're going to use a trig identity that looks like this. We're going to say that the sine of 2, I'm going to use alpha and beta here for the angles, where this is going to be alpha up here, and the omega t is beta. And the trig identity for this is that sine alpha cosine beta, there's a plus here, right? Yeah. Right, plus? Plus. Yeah. Cosine alpha sine beta. And we're going to do this identity for both terms here. So we're going to get a really long expression here when I do this. Let's get it all out. There's going to be an A in the front here. Okay, what is going on? Something. Oh, that's what was happening. All right, never mind. So this is going to be A sine kx cosine omega t plus a cosine sine omega t. And then that's the first term. So that was this term right here. The second one, since we're adding these things up, so again, this is y1 plus y2. So the next one here is going to be an a, and this one we're going to have, oh, this is a minus sign here. If we had a minus sign here, there's a minus sign here. So let me fix that. Oh my gosh, what did I do? Can I control Z that, please, Zoom? I love Zoom. It's the best. It's the best. I can't seem to select it. Okay, there we go. Oh, perfect. Perfect. Okay. Whew. Avoided a catastrophe. I mean, it would have took like a few more minutes, but whatever. All right, so the next part here, we're going to do the plus one. So it's the same stuff, but with a plus sign here. And so guess what happens? See you later. Cosine kx sine omega t. You're gone, and you're gone. And we are left with this pretty darn cool relationship. A 2a sine kx cosine omega t. Now check this out, though. The first part of this is, think about it as the coefficient for the cosine function, right? Let's go back to my slides here. So let's look at this picture. All right, so that's the formula we get. And if you look here, what that is, it's a sine function. So all the black lines that you see here, those are the sine functions, right? But what's happening is it's being modified by this time variable cosine. So what happens is the wave amplitude grows and shrinks. But it's a sine function, a stationary sine function with a change in amplitude. The amplitude varies, okay, in time. And that's really a nice way to think about it. In fact, actually, now that I just said that, I think I kind of fouled up what I was actually trying to say there. This should actually view this as 2a cosine omega t. That's really what you want to do. And then the back end of it is just a sine function. So that's a stationary sine function. And then the first part of it is your time variable amplitude. Okay, so that's kind of neat. Now what happens here is this. These parts that are red right here on the x-axis, these are called nodes. These are called nodes. These are locations. There's one here. These are locations where the standing wave has no amplitude at all. And that occurs when that sine function is 0, right? So that means kx, which is the argument of the sine function, has got to be multiples of pi. So if you solve for x, we get n pi over k. Now k is wave number. So if I replace that with what wave number is, we end up with this relationship right here. N lambda over 2. Because remember, k, that's 2 pi over lambda. So the pi's drop out. 2 stays in the bottom. And so what this says here is that every half wavelength, so this is the half of the wavelength here, and there's a full wavelength there. Those are where the nodes are. So the sine function is, it comes up and goes through the x-axis and comes down and comes back up. But at every half wavelength, half integer wavelengths is what the nodes are. Okay, these points in blue here are called antinodes. They're the points of maximum displacement here. And so usually these things vibrate very, very rapidly, and it looks like the wave is stationary. That's the idea. So it look like the wave is stationary. It's actually oscillating very rapidly. They're usually very rapidly, so you can't see that too easily, but it just looks like a stationary wave there. Now, these antinodes occur at maximum values, right? So that would be kx, and this would be at basically pi over 2 values. Instead of being pi, it'd be pi over 2 values, but we got to make sure we skip. Oh my goodness. My drawing pad is a little temperamental right now. This would be at 2n plus 1 pi over 2. 2n plus 1 is going to ensure that we only have odd numbers. And so when you solve this, we end up with a 2n plus 1 over 4 times lambda. And so if you put in, say, 0, these things will start at 0, right? You put in 0 here, you have lambda over 4 as an antinode, which is correct, right? And then if you put in a value of 1, you get 3/4, 5/4, 7/4, and so on. So it's basically odd integers on the top, and just make sure that you put it at the amplitude of these things. So it always occurs at a quarter, multiples of basically a quarter of a wavelength, not counting the nodes though. All right, so that's kind of crazy here. All right, so that's our standing wave stuff. Let's keep moving on here. All right, so when you look at this, what is the wavelength of this standard wave pattern? Okay, so say you see this standard wave pattern here. What would be the wavelength of this? A lot of people saying C. It is C. Congrats. A lot of people will see the one lobe or something, but so this one's an open standard wave, we would say, because at x equals 0, the amplitude starts off at a positive displacement here. Big, there's node not right at x equals 0. Okay. Now, by the way, go back here for a moment. At the bottom here, the 2a. So the interpretation of the 2a down here is that the amplitude of the standard wave pattern is double that of a single wave. Okay, just remember that. In fact, your book actually just labels it as A with a subscript of SW for standard wave. They probably don't even have the 2 in the front here. But that can be a little deceptive. I don't like to do that because people don't make that connection normally. Okay, so let's combine all these ideas that we have now together here. Now, what are we doing on time? Okay, so what I'm going to do, I'm going to go through these 2 examples, and we'll take our break because we're about an hour from now. All right, very long string has a linear density of 5 grams per meter. Let's just jump right to my example, though. Here it is, right here. We got linear density, and we have a tension. So I'm just going to go ahead and before I even read the rest of the problem, I'm probably going to have to know what the speed is, right? So let's just figure that out. Our tension's 8. The value for mu is 0.005 kilograms per meter. And you put that through, and we get a speed of 40 meters per second. Great. We have a frequency of 100 hertz, amplitude 2 millimeters. Fantastic. So I can figure out my wavelengths here. So I'm going to use the fact that lambda is V over F. I put my 40 over 100 hertz, and we get that our wavelengths are 40 centimeters. What is the node spacing along the resultant standard wave pattern? Nodes are separated by half a wavelength. If we have one at x equals 0, there'll be another one at lambda over 2. There'll be one at lambda, 3 lambda over 2, 2 lambda, and so on. So that node spacing would be 20 centimeters then. And that's the same as the antinode spacing, by the way, too, right? They're the same. So that takes care of part A. What's the node? So you're just figuring out the wavelength for that. What is the maximum displacement of the string? Okay, check this out. the string has 100 hertz waves with amplitudes of 2 millimeters. The maximum displacement, because it's 2 waves and it's a standard wave pattern, will be 4 millimeters. Okay, because you're going to be doubling that, because at your antinodes is where you have complete constructive interference, you'll have double the amplitude. Okay, at the nodes, it's complete destructive interference. There's no amplitude there. Great. Let's do the next example. Okay, a guitar string is plucked and creates a stand-in sinusoidal wave with an amplitude of 0.75 meters. Okay, now that, wait, creates a stand-in wave. Okay, so the amplitude is 0.75. Okay. That's the 2A. Just to be clear about that, that's the 2A. All right. Frequency is 440 hertz. The wave velocity is 143 meters per second. Find the equation of the stand-in wave. Well, that's easy, right? We got our equation right there. 2A sine kx cosine omega t. We got to figure out what our k and omega are here. So omega is very easy to get. It's 2 pi times the frequency. So 2 pi times the frequency, which is, you see right down over here. Let me annotate this. Yeah. Let's get a lavender in here. I'm loving the lavender right now. All right. So the angular frequency is real straightforward. It's 2 pi times frequency. So we got that. That's the cosine 2760t here. And then we go back here to look at what the wave number is. It's omega over v. So 2 pi f over v. V is what, 143. So all these numbers here compute to 19.3. So that's my function down here. Notice here that we're told that the standard wave has an amplitude of 0.75 millimeters. So that's not the value of A. That's the value of 2A. That's the value of 2A. So I have the 7.5 times 10 to the minus 4 here. That's my equation. Where are my nodes? All right. Nodes, remember, occur at half integer lambdas. All right? Half integer lambdas. So I'm just going to substitute. So that's, it's just n lambda over 2. I don't have lambda. I mean, I could calculate it, but I'm just going to put it in terms of the wave number. So that's why I'm doing a substitution here. 2 pi over k is lambda. The 2's drop out, and I get n pi over k. And I just plug in my value for pi and k, and I get up with 0.1625 n. Okay, n. So the assumption here is n is integers, right? 0, 1, 2, 3, 4. You know the integers. There you go. So that's it. And then we can find the maximum speed and acceleration of the string. This goes back to our equations from the first time. Maximum speed is omega a, and acceleration is omega squared a. That goes back to physics 110 and oscillations. And the string, again, we're talking about the standing wave. So I multiply those numbers together, I get 207 meters per second. That's fast. That's pretty darn fast. But this frequency is pretty gnarly, though, so that makes sense. And the acceleration is given here as well. Okay. So it's a matter of, remember a lot of those equations from a while ago. That's a big part of this thing. Okay, so this is a real quick snapshot of a standing wave pattern where we actually have an entire wavelength incorporated into this. We have names. This is called the second harmonic. Now, we're looking at like strings right now. And what's important about looking at things from a material standpoint is that there is a fixed distance, right? That's the thing, is this string has a fixed distance. So with a fixed distance, there are only going to be certain frequencies that can produce standing wave patterns. Okay, for example here, whatever frequency is produced in this particular pattern happen to fit 3 nodes and 2 antinodes in. But if your frequency was different and you can't fit, a whole number or half number of wavelengths in, you get kind of jumbled garbage, you know. So a fixed length, there are certain frequencies that work. Okay. So this one in particular is called the second harmonic. There are two antinodes, two harmonics. Second harmonic. Okay. You can have the first harmonic, which would be one antinode in there. That's it. All right. So the one at the top here would be considered the third harmonic. The one below that is a fourth harmonic. You're basically counting how many antinodes you have here. Okay. Higher frequencies, if the frequency is higher for a given wave speed, remember the wave speed is set by the tension, right? Once you made your rope and you put it under a certain amount of tension, that wave speed is set in stone. So by alternating the frequency, you are changing what the wavelength is. Okay, and then the question becomes how many half wavelengths can you fit on the length of the string? That's sort of the idea. All right, so say we take our string and we want to figure out what frequencies are going to produce a standing wave pattern. Now, the idea here is standing waves are formed. There's not a lot of place to write equations here, but remember, we came up with this for our nodes. The idea was that the x positions are n lambda over 2. What we're going to do here is we're changing our x, right, to be L, the length of the string. And then we rearrange this to solve for lambda, which is this relationship right up here. But what we really want to know are the frequencies. So we use a relationship that speed over wavelength is how we get a frequency. So our frequency equation ends up being this thing right here. NV2L over 2L. And so you put in, whole numbers here. 0 doesn't make any sense, obviously, so we don't do that. But integers, whole numbers, I should say, really. 1, 2, 3, and so on. This tells you what frequency. So if you have an n of 1, okay, we call that the fundamental frequency. Fundamental frequency. And that occurs when your value for lambda lambda is simply 2 times L, right? And so you get a half wavelength in here, okay? This one down here is a full wavelength. This is n equals 2. So the frequency there, we call it the second harmonic. And this is kind of a really strange terminology here. It's used a lot in for like wind instruments and things like that. But n equals 1 is the fundamental frequency. N equals 2 is what we call the second harmonic, and it's what's called the first overtone. First overtone meaning the first frequency past the fundamental frequency. N equals 3, third harmonic, second overtone, and so on. So the idea is that each one of these values for frequency are increasing, but they have to increase in very precise increments. If we have a frequency that's between A and B, we're gonna get a bunch of nonsense. We're not gonna get a standard wave pattern because the idea that a wave's going left and right at the same time is not occurring here. There's gonna be some kind of weird phase shift occurring if things are not at the right intervals. That's what I'm saying. Okay. So What is the mode number, the value for n for this standing wave pattern? What do you think? I think you're all right. Good. You just count antinodes. Okay. And the number of nodes is always 1 plus. All right. Fantastic. All right. This one here. Read over this. I'll be back in 1 minute, actually. Put a letter in the chat. I've left my water downstairs. Hold on, I'll be right back. All right, so what we got here? We got tension is reduced to 1/4. That means the speed goes down by a half, huh? The frequency and length are unchanged. So if the speed goes down by a half, excuse me, that means the frequencies, you're going to be increasing those. All right. A lot of people saying A, but it is C. So the idea behind this is by reducing the speed by half, right? And so now the frequency is, oh, actually we're keeping the frequency unchanged here. Ah, that was the difference. So the frequency is not being changed. If the frequency is not being changed, then if we look at the equation here, and that means we're going to have greater values of m here to get the same frequencies out of this. So we're going to have more antinodes then if the tension's reduced, but the frequency stays the same. Okay. All right. So if we combine those concepts together, so if we put in, for speed, because the equation is what, n v over 2L. If we put in place of v what that would be on a string, say it's a musical instrument or something, and we put an n value of 1, then the fundamental frequency would be given by this formula right here. Okay. And so if you were to increase F, the tension, you're increasing the frequency. I mean, if you played guitar before, so I play guitar, you tighten the string, pitch goes up, right? You hear the frequency go up because you're increasing the tension of it. And then when the strings are, not too taut, they're a little loose, and you get a much lower pitch. All right, so let's do an example here. Adjacent antinodes of a standing wave on a string are 15 centimeters. Okay, so the idea with antinodes is they're separated, right, by lambda over 2, just like nodes are. So the lambda here is apparently 30 centimeters. We have an amplitude. We have period. So if we have period, we have frequency. All right. How far apart are the adjacent nodes? Well, that's simple enough, right? Let's get to my example here. What? Where are we? There we are. Let's do this. Let's zoom in a bit here so I can see what I'm looking at. There we go. All right, so if the antinodes are spaced by 15 centimeters, then the nodes are spaced by 15 centimeters. The distance between nodes and antinodes are half that, so 7.5 centimeters. Simple enough. Find the wavelength, amplitude, and speed of the standing wave. Okay, well, the wavelength. So what's the difference between the standard wave and the traveling wave? The only real difference is the amplitude, right? The amplitude is going to be, for the standard wave, it's going to be double of the traveling wave. So what are we told here? Particle on an antinode oscillates with an amplitude of 8.85. That's the standing wave. The 0.85, that's the standing wave amplitude. So we got to half that to get what the amplitude is for the traveling wave. Let's scroll down a bit here so we can see that. So that's the 0.425 we have down here. Now, the wavelength and the speed will not change for these things, right? Because the wavelength is based on wave number, You could also say it's based on frequency since the speed is set here. So all those things are the same. Really, the only difference between the two things are their amplitudes. Find the maximum speed of the string. Now, this if it wasn't clear, the maximum speed of the string is the wave going up and down. And that's given by omega A, where A is the standing wave amplitude. Omega can be determined by 2 pi over the period. So we have period information here. And so we get a 71.2 centimeters per second is what I put in for that. All right. Pretty straightforward stuff. Great. All right, moving on. All right, let's get to this example now. Okay, what do we got here? Notice the consistency in these problems. I mean, every time we encounter these problems, the first thing I'm doing here is I'm looking for all my wave information, right? What's amplitude? What's period? Right? What's frequency? What's lambda or whatever. I mean, once you find those things, it's just a matter of juggling all these equations and trying to figure out what goes where. So what do we have here now? Standing wave on a wire is amplitude. Okay, so that's the standing wave amplitude. Got it. Got omega. Got K. The left end of the wire is x equals 0. Well, this is pretty straightforward, I guess, right? At what distances from the left end are the nodes of the standing wave? Okay, so those go by half wavelength multiples, right? So that's what the nodes are, half wavelength multiples. So instead of wavelength here, I'm going to put in my wave number because that's what I'm given here. Although you can just work out your wave number if you want, your lambda if you want to. Perfectly fine to do that. But I want to put it in terms of wave number because I get a nice relationship here. The 2's drop out. This ends up being n pi over k. K is given in terms of pi, which is very nice. It's 3/4 pi. The pi's drop out. We end up having 4/3 n. And so we start at x equals 0. And then at 4/3, we have a node. At 8/3, we have a node. And 12/3, we have a node. And so on and so on and so on. The answer really would just be, 4n/3. You don't have to specify the different modes here. Antinodes are going to be given by odd multiples of pi over 4. This is the equation we developed before. Same deal. Put this in terms of k. Clean this up. And we get 2/3 times odd integers. Now, notice these. 2/3, 6/3, 10/3. Guess what? Those occur right in the middle of the nodes. Perfect. That's how you can tell. It's a little sanity check. Make sure I'm getting my right values there. What is the node to antinode distance? Well, you could just subtract any adjacent nodes, right? So 4/3 minus 2/3 is what I did here. And it's apparently 2/3. 2/3 meters. And I automatically know what the wavelength is, right? Multiply that by a factor of 4. That's it. The wavelength is 8/3. 8/3. Right? And the second harmonic is always equal to your wavelength, so you can always see it from there too. All right. Any questions so far about anything here? Everybody's so quiet. I mean, this stuff's a matter of just, like I said, juggling equations. The concepts are not too challenging here. I mean, the only concept we really have to work with is, just being able to specify, what the zeros of the sine functions are and things like that are the maximum values. All right, so I think we got another, not another example here, but are going to apply this to sound now, actually. So I'm going to do another application of this as it relates to sound, because here's the thing. When you have the standing waves on the string, you're dealing with fixed ends, right? Fixed end, fixed end. So your nodes are set, basically your nodes are set. When you have sound, though, sound's a little bit different because sound can have open ends. So you don't have to necessarily have fixed ends. You could have open ends there. And so things work a little bit differently. So this is an exercise really in establishing properly where your nodes and antinodes are for things here. Okay, so the most common example of this is like a musical instrument like an organ. Again, we have these labs. When we have labs, we have a really neat lab where we have these water columns, and we ding tuning forks inside these air columns with water in them, and you can figure out nodes and antinodes like that. It's kind of a neat thing, but yeah, we're not doing that. All right. So what's happening here is the waves that are occurring here, these are basically pressure waves. I mean, that sounds effectively, it's a transmission of pressure. And so we talk about nodes and antinodes here. The waves are traveling through, say the organ pet, for example. And the interpretation of what a node and antinode is a node would be, it's a destructive interference. So if you were to put your ear at a node, you wouldn't hear any sound. As opposed to the antinode, which is, the complete constructive interference, and the sound would be at its largest volume, basically. So that's what we mean here when we talk about nodes and antinodes. The pressure waves are either combining constructively, destructively to do this. So now, let's see, what are we working on here for the open pipes first? Okay, so we're going to work with an open pipe first. And what that means is that when you have an open pipe, you have antinodes on both ends. Okay? Open end is an antinode there because the idea behind this is the cancelization. So if this was a closed, for example, if this was closed here, okay, then a node would be established there. It would be just like a string, right? You have fixed ends, you have nodes at the ends, but when you have open ends like this, you have antinodes. So, but the patterns work very similar here because here we have both open ends. It's like having two antinodes on both sides is really not any different than having nodes on both sides. So the equations all work pretty much the same. The fundamental frequency is given by NV over 2L. L is the length of the pipe here, and so N being 1, that's the fundamental frequency. Same thing for the string. All right. So if we have, higher frequencies, that's going to produce different harmonics. So if we up the frequency, with these integer multiples here, we can fit, more antinodes and nodes in there. So you're simply doubling, tripling, and so on. So this is all familiar stuff. Now, the closed end is a little trickier because for the closed end, what will happen is the left-hand side of the pipe here, which is open to the air, obviously, is an antinode, but now the closed end becomes a node. And so the equations work differently here because now we have to ensure that our wavelengths, right, are like quarters, basically, quarter multiples, like odd multiples, I should say, of the length of the pipe. So the fundamental frequency here would actually be given by a quarter wavelength here. So we get V over 4L for the fundamental frequency of this. And then for the next step, again, we're doing odd integers here. Now, they show a value of n up here. I like to do the 2n plus 1 thing. So when I have the equations, I think your book sticks with it like this, though. Your book likes to keep the n value, because the problem with that, in my opinion, is this. You have an n here for the open pipe, right? And it's like, okay, well, that's integers, or whole numbers, 1, 2, 3, 4, and so on. And then they use the same value, they use the same notation here, n. But then it's odd integers, right? And the problem with that is, students see that n and they just think it's 1, 2, 3, 4, and so on. So I you know, I want to, you know, I think it's better to state things like 2n plus 1, you know, v over 4l. And then you use the same values for n. That's it. Use the same values for n. So, all right. Oh, you know what? It actually makes more sense to not do that. Sorry, it makes more sense to actually make this not a plus sign, but a negative sign. Right? Yeah. You should make this a negative sign, I guess. It should be negative. Well, because the idea is you don't want to use 0. It doesn't make any sense to use 0. So if I use 0 here, you get your first harmonic, but this should be a minus here. So if you put it as 0, you get nonsense. So 2n minus 1. I mean, that's also odd, right? I think that makes more sense here, though, because you don't want to use 0 for n. 1, 2, 3, 4, 1, 2, 3, 4. Just stick with that. Okay. So here, the third harmonic. Okay. So we had the fundamental frequency right here. This is our third harmonic. What the value of n is 3. Okay. There's no second harmonic here. There's no second harmonic here. We can't do that here, basically. So either we have one antinode like this, or we have two antinodes like this, but you have a truncated wave here, right? So when we put in the values for n here, you got to realize, though, is that this second value is n equals 3. The value of n here is going to match up with how we name things here. So if we get a 3 in the front here, right, that's third harmonic, fifth harmonic, and so on. Okay, so open tube. So we have open on both sides of air. What is the m equals 3 standing wave going to look like here? What do you think n equals 3 standing wave is going to be? Both ends are open here. First thing you want to think about here is this. Open ends, what's on the ends? Are they nodes or antinodes? And then from there, you want to determine how many of those you got. It says M here, just to be clear. M and N are interchangeable. Some of my slides involve M from a different textbook, and I just haven't changed them. All right, good. So it's definitely B or D, right? And then here, what do we got? It looks like we have 3, and we have one. Yeah, we have 1.5 wavelengths basically. So 1.5 wavelengths. You're looking at the number in the front there. That looks like. Well, that would look like, honestly, it would look like this situation right here. Open at both ends, right? And so that would be n equals 3. Okay. Sounds good. Okay, if you close up one end, again, think about where do antinodes and nodes exist here, and what should the n equals 3 look like? Careful about this one. Be careful. No fooling you guys. You got it. You got it. Okay, so it's got to be B or D, because you need a node at the right-hand side. And we just got through talking about this. The n equals 3, that's the, that has a 2 antinodes in there, right? That's the situation back here, right here. It's the third harmonic. N equals 3 here, but that produces 3/4 of a wavelength, basically. Right? So it's a matter of, you're looking at, lambda over 4 odd multiples. Right? Okay. Fantastic. All right. So one last example. How are we doing on time? Are we okay on time here? Yeah, we're doing great on time. Let's do this one last example. And, this is I'll be honest, this is an awkward subject. But here's the thing. Because there's a lot of random ideas that seem to be kind of disconnected. But definitely don't take this chapter for granted because a lot of these ideas, just pop up in modern physics. I mean, basically, rethinking about a lot of physics in terms of waves, I mean, really changed physics. I mean, a more developed electricity and magnetism was created with thinking about electromagnetic disturbances as waves, wave behavior. And then thinking about particles and matter as having wave-like properties. Thinking about light as a wave and that it can interfere, can produce standing waves and all that stuff. So you're going to see these ideas pop up in a lot of places, which is why I like to go and do this stuff now. All right, let's get to this last example here. Okay, now the word stopped. The word stopped means the end is closed, all right? End is closed. So, one a day, huh? What kind of sentence is this? Okay, I guess there's no a. One day, on a day? I think it's meant to be on a day. Yeah, you know what? I think, in my professional opinion here, which I can't really claim to have for anything grammar related, I think this is supposed to be on a day. On a day when the speed of... Boy, I'm just a wreck here. Look at this. On a day when the speed of sounds... All right. I think what happened is when I created this example, it was like the end of the lecture, and I was like, I just got to get through this last one here. All right. On a day when the speed of sound is 345 meters per second, the fundamental frequency of a particular stopped organ. Okay, so that's the one that has the node on one side and the antinode on the other side. And so that fundamental frequency is going to be a quarter of the wavelength. All right, and so that frequency is 220. So here's my equation right here for the fundamental frequency of a stopped pipe. Okay, V over 4L. And so that will tell me what the length of the pipe is, right? Because I have V, it's the speeds up there. And the frequency is given as 220. My value of n is 1, and we solve our length here, and that is at 0.392 meters. Excellent. What else do we got going on here? The second overtone of this pipe has the same wavelength as the third harmonic of an open pipe. What? Okay. So the second overtone of this pipe, now the second overtone of this pipe, that's going to be an n equals 5 value. Because remember, when it says second overtone, that's the third frequency in the sequence. So we have our fundamental frequency, that's n equals 1. We have the second harmonic, which is the first overtone, and that's n equals 3. The second overtone is the third harmonic, and that has a value of n equals 5. Okay. Is that confusing enough for you? Second overtone, third harmonic, n equals 5. I didn't make these rules. I didn't come up with these conventions. Pretty gnarly stuff, to be honest. But anyway, that's one thing you really got to keep in mind for that stuff. Anyway, so if my value of n is 5, then that I'm just multiplying the fundamental frequency by 5 here. And that would be 1100 hertz. Great. Now, that's what that frequency is. And it says here that the second overtone of this pipe is the same wavelength, same frequency. That would mean the same thing, right? If the same wavelength means same frequency, because the speed's the same. As the third harmonic in open pipe. Okay, what's the third harmonic in open pipe? Well, open pipe has n V over 2 L. And the third harmonic, now remember for the open pipe, you have antinodes on both sides, which is like having nodes on both sides. And so the third harmonic will be an n equals 3 value. And the idea here is that I'm setting the third frequency to be equal to 1100. I plug in my value of n equals 3 here. I know my velocity. I solve for my length here, and the length is 0.47. So it's actually two different problems in one, using the same speed and then matched up the harmonics here.